Okay. Yeah, I mean, um, Malcolm already introduced a lot of the challenges and the topic generally, how machine learning can be used to develop all sorts of auditory models and all the challenges that come with this. I think what I want to do is to take it a bit further and a step further and just say how we can go beyond what has been done in terms of models of the cochlea and of the periphery, but also before really getting into really developing large models that model the whole complexity of going from sound to perceptual outcomes essentially. And this talk is going to be more about how large-scale electrophysiology can be combined with deep learning to develop accurate models of the brain, essentially. So I don't know, shall I start?
Yes, please go ahead.
Okay, perfect. All right. I'll just start with a very brief introduction of the auditory system. I mean, we're all well aware of that by now. But when a sound essentially reaches our ear, it travels through our ear canal to the middle ear and the cochlea, and there it's analyzed across frequency and is transformed essentially into electrical activity, which is passed to the brain and is utilized to generate auditory perception. And already Malcolm explained that the work that has been done and researchers have tried to approximate all these complex sound transformations essentially that take place and constitute hearing. And there have been many models of the auditory system that have been developed that have helped us significantly to understand how we humans perceive and process sound. So, more or less, the sound transformations that take place up to the level of the auditory nerve are quite well understood by now. And again, this is more in line with what Malcolm said about all the models, the more biophysically realistic models that have been developed for the cochlea, for example. And these models are still widely used across academia and industry and essentially can simulate auditory processing in various levels of details, but also for different types of hearing loss. And more recently, machine learning has also made these models much faster and differentiable, and this has facilitated their use in the development of new sound technologies such as hearing aids and the enhancement models that Malcolm explained. But models of the auditory processing in the brain are much less accurate still and have very limited real-world applicability. And this is mainly because the way auditory information is integrated within the brain is much less understood, and the sound transformations that take place are too complex for models to be designed by hand, as in the case of the cochlea. So brain models have been typically developed to learn quite constrained transformations from very limited neural data sets. But recent advances in deep learning and large-scale electrophysiology have created this new opportunity to model sensory processing in the brain with high accuracy. And what we've done in the last few years is that we've recorded a lot of large-scale neural data sets from the inferior colliculus of anesthetized gerbils, an animal with similar hearing sensitivity to humans. And this in response to broad data sets of sounds that include more than 10 hours of speech, music, ripples, etc. And what we do is essentially we play all these sounds to our anesthetized gerbils and we record their multi-unit neural activity in their brain using custom design electrodes. And the responses that we get look a bit like this, where we get essentially for these simple speech segment responses with high temporal resolution, but also with spatial resolution that captures the whole tonotopy essentially of the IC across both hemispheres, uh, essentially getting from low frequencies to more high frequencies with high resolution. So now that we have these kind of data sets with the required resolution and for all these complex sounds, we can use deep learning to try and describe the mapping from sound to neural activity and derive accurate brain models. To do that, we developed a framework that combined recordings from different normal hearing animals to start with, and this using a convolutional encoder that maps sound waveform to a generic latent representation of what they're processing, which essentially extracts the shared latent dynamics from the different brains. And then this is followed by simple linear readouts that are used as decoders to map this generic latent response to the individual neural responses of all animals. And the result is ICNet, a deep neural network model of central auditory processing, which essentially takes as input sound waveform and produces activity patterns across thousands of neural units with millisecond precision. So this framework that we designed enabled ICNet essentially to describe the full statistical complexity of neural activity in the brain. And because it is based on convolution, it's also quite fast to execute. But when building deep learning models of sensory system, it is crucial to evaluate their performance on new inputs that were not part of the training and ensure that these models can generalize well to any sound. So here just provide a simple visual example for two sounds that were unseen during training, speech in quiet segment and moving ripples. As you can see from the spectrograms already, these have very different frequency properties, with speech, of course, having more low frequency content and the ripples having only high frequency content. And what we see when we record the responses to the sounds in the IC is that we get responses that look a bit like this. So this is across different units from different brains sorted by their characteristic frequency from low to high frequency. And we see, for example, for speech that the responses do look a lot like the spectrogram. But when we look at the ripples, we see something completely dissimilar, essentially, to the spectrogram. And this demonstrates more all these nonlinear sound transformations that actually take place in the brain and transform the sounds. But in any case, the model we developed did a good job in capturing all these complex transformations and provided a near perfect simulation of neural activity for these two sounds. And we've also quantified all that, of course, across a wide range of sounds and individual brains. And we saw that IceNet was able to capture most of the explainable variance and correlation across sounds. So we also designed ICNet so that the encoder can provide essentially a baseline representation of normal auditory processing that can then be used to predict neural activity for any normal hearing animal. And to test this, we used neural datasets recorded from new animals that were not part of the training and updated only the decoder weights of ICNet to predict the new responses, always keeping the ICNet encoder fixed. We tested these newly trained models on a completely new set of sounds that have also been typically used to evaluate neurophysiological phenomena of the auditory midbrain. And what we found is that ICNet performed very well even when using as little as 3 minutes of data to update the decoder weights for the new animals, and that it could also replicate a number of physiological phenomena such as frequency tuning and temporal dynamics to pure tones, but also more complex phenomena such as the tuning to amplitude modulation sounds and also dynamic range adaptation. I won't go much into the detail about all that. I will just skip to the fun part, which is after establishing all these details about making sure that ICNet is an accurate model of the auditory brain, we can now put it to the test for different applications, as this is essentially a proof of concept for the broad applicability of models like ICNet and also essentially leads to what Malcolm talked about what the McDermott lab has done over the years, which is essentially to use realistic frontends to simulate neural activity or some biophysically relevant representation that can then be used to train deep neural network backends that do specific tasks, such as speech recognition. But using essentially ICNet and this kind of brain models as the frontend, maybe can go a bit beyond using just cochlear representations, as essentially this can impose the constraints that are also faced by the brain to these deep neural network models. So what I'm showing here is a simple example. I essentially trained a convolutional neural network to predict speech recognition using ICNet as a frontend. And this either using essentially the ICNet or using a MEL spectrogram, which is more typically used. And both systems showed similar performance essentially, but there is a benefit at low SNRs, at more noisy conditions. And this is a bit promising for actually building more noise robust systems. And hopefully this can also lead to models that can be trained without the need for complex architectures and large training data sets that are fitted essentially to specific tasks. But also getting back to also what Malcolm was describing about the individualization, ICNet can also be conditionalized like other models so that it individualizes essentially the hearing loss profiles of listeners to reflect hearing impaired processing. And again, I trained the model of the previous example to predict speech using both a normal hearing but a hearing impaired ICNet frontend. And what I show here again is that using these pathological brain features results in much slower speech recognition. And this again suggests that the auditory brain features that ICNet provides might be a good proxy for simulating perception in artificial systems both before and after hearing loss. So now I'll go more into detail about all these enhancement models and how essentially models like ICNet and deep neural network models of the auditory system can be used to improve hearing technology and engineer better hearing aids. So the idea here is simple. This has been my main research focus for the last few years. If we have models of deep learning models of normal hearing and hearing impaired processing, we can then train new sound processing strategies that essentially restore impaired neural activity back to normal. And we've called these models AidNets. And what an AidNet essentially learns to do is to compensate for all peripheral and central auditory changes after hearing loss, up to the level of the IC in our case. So here I just provide a simple example from the many AidNets I have trained the last few years, which shows the restoration of neural responses for a noise-exposed gerbil with a moderate high frequency loss. So what we typically look at is how similar impaired responses are compared to normal responses, and we look at metrics such as correlation. So when we look at correlation between hearing impaired activity and normal hearing activity, we get values around 0.7. And then when we compare the activity across different normal hearing brains, we get much higher correlations. Responses look much more similar. So what we're trying to do here is to build this kind of sound processing models that can provide the optimal sound processing to restore impaired neural activity back to normal. And that's what we've seen so far. We can train AidNet models that get correlations back to normal and on normal levels. And most importantly, these seem to be doing much better than standard hearing aid strategies. And the same holds when including also these example speech recognition models that I explained before in the hearing aid training framework. So again, we see that an AidNet can be trained to restore even simulated phoneme recognition close to normal levels. So I think I'll skip the conclusions and future perspectives. What I'll try to say, and we can just jump in the conversation, is that I tried to show here how also we can use large-scale electrophysiology with deep learning to engineer better models of the auditory brain. And I think the exciting part here is that we're getting closer to actually building this kind of complex models and using them for building advanced models that include additional aspects of auditory processing, such as behavioral modulation, higher level computations, similar to the speech recognition task we talk about, and also advancing existing sound technologies such as hearing aids, with a hope that these kind of models can make machine hearing systems that perform more and more like humans. So yeah, that's it from me. I just had a thank you slide for all the people that made this work possible. And I should also say that our model is publicly available on my GitHub page.
Great. Thanks, Fotios, for your talk and overview. And I think with now time for questions for both of you. And in the
Shall
chat
I stop
already...
sharing, or how
yeah,
do you
please
want?
stop
Okay.
sharing. I think that's good that we spotlight you. There is in the program a mini break of 5 minutes, but I suggest that we also use the time for these questions, and then Brent can take over with his talk. And there were some sort of question in the chat, so let's start with this one, and that's for Malcolm from Roger Miller. So he thanked you for the great overview of AI models, and he asked for some more comments about this dynamic range issue. Is it unique to models of the auditory system, and how do we deal with this issue in the best possible way, as opposed to using well-known solutions applied to image analysis?
I don't know. I'm sympathetic to Josh McDermott's approach of giving up on the cochlea and letting the cochlea do all the dynamic range stuff, because neurons are essentially 8-bit devices, which is why visual systems work so well. But I really want to model the impaired cochlea, so I'm not quite sure what to do. I'm really bothered by the idea that ReLU, which is essentially an absolute value, works so well in auditory in deep neural networks, and that's provides no compression. There's nothing level sensitive about a ReLU. And you can combine ReLUs with appropriate plus and minus signs to get an arbitrary, compression, but it's very painful. So we've been looking at building differentiable models of a realistic cochlear model that includes nonlinear filters. And we can differentiate them, we can see changes, but it's painful. And I think the jury's out as to whether an approach where you model the cochlea as a black box using conventional neural network, or whether you go to the expense of doing a biophysically plausible, physical model is going to be more effective. I'm putting my money on biophysically plausible, but
Do I then understand that you would suggest that instead of the current artificial neurons, you try to improve those artificial neurons to make them more biologically plausible?
Well, we're actually building it with filters, and I mean we're building neural networks that model the filters that we use conventionally. So Dick Lyon's model has conventional IIR, infinite impulse response filters, and we can differentiate those. Lowell Carney's model has a much more complicated approach, and that's going to be harder to differentiate. So, I wouldn't say we're just modifying their neural networks. We're building whole new networks in systems like JAX that let us build arbitrary, nonlinearities and feedback paths. And so that's our
okay. Thanks. Yeah, great for explaining that trade-off as well. Then continue with a question for Fotis from Mark Settler. He thanked you for the nice talk and asked, have you tried inserting a separate peripheral auditory model stage before ICNet? An animal model, you could potentially try matching the peripheral parameters to individual gerbils' hearing loss.
Yeah, that's a good question. I mean, we haven't explicitly tried that, and it kind of leads back to also what Malcolm was just talking about. I think what we have tried is, and we still have in our model, like the first stage being, for example, bandpass filters that can be tuned to learn something that resembles essentially whatever the cochlea is doing in terms of frequency analysis in a very simplistic way, of course. And it is learning something like that. It is learning like broader filters at lower frequencies and sharper filters at higher frequencies. But the truth is that, like, even if you, I mean, going back to Malcolm's point, even if you don't do that, and even if you do, like, just, I don't know, stack a couple of layers, a couple of convolutions layers or whatever, the model will still perform well and it will still learn something that can do something, or kind of like circumvent doing all that explicitly, but learn to do something that like approximates essentially that. So to answer Mark's question, we haven't tried doing this explicitly. Don't see anything wrong, bad with this. Like, I think it might actually benefit what we learn. What I wanted to say for the hearing loss part and for the individualizations, that what we've tried to do on this part is to not impose any specific assumptions about what the hearing loss needs to be. So we have a preprint now out that is essentially conditionalizing this ICNet model to learn how hearing loss can essentially influence the output. And you can do it with audiograms, for example, which we know they're not the whole story for hearing loss, but you can actually do that in a better way, even where you constrain the model essentially to learn just a few parameters that corresponds to hearing loss. And we have, for example, like a lot of animals with different sorts of hearing loss, and then the model can learn to find these hearing loss parameters, like this small set of parameters from the data, And the whole idea afterwards is that when a new person, for example, comes in the clinic and you want to optimize, in the case, for example, for the hearing aids models that I showed, a new model, you just do this whole human in the loop optimization where you get perceptual answers from the listener to get to what essentially a fitted, let's say, model to the individual hearing loss profile.
So do I get it right that the animals help you in creating this pre-trained model and then you fine-tune it on human data?
In a way, yeah, you can think of it in this way. I think even
Wait,
sorry, go
given
ahead.
the time, I think we can
No,
continue
you're
this
right,
discussion,
you're right,
but I
you're
see
right.
another really great question here from Anko Rivas. So he asked about the 8net. Is it just another neural network model, and are the parameters modified for application in hearing aids or implants? And you already alluded to that you see that this applicability of your models. Please comment on the parameters of 8net.
Yeah, it is another deep neural network model to start with, although we do try to constrain these models to be as lightweight as possible. I mean, to the extent that this is possible, of course, but like it's still like convolutional neural networks with small encoder and decoders that do some light sound processing, or we try to constrain them at least to do some light sound processing. So there is this kind of constraints that go into the optimization as well. But the idea, yeah, it's that you essentially learn models that can then be optimized for different individuals. And we're also planning, essentially, now we're starting our first batch of listening experiments with hearing loss individuals to see whether these are translatable, essentially, to humans and what needs to be done further.
Okay, great. I had also another question for you, Malcolm, about these enhanced models. I wondered, instead of modeling impaired hearing, are there also models for superhuman hearing? And could that help us maybe also with the models of McDermott in mind? Do you think that's feasible, realistic, or should we stop dreaming about that solution?
You know, the easy answer is I'd be really happy to model and make abnormal cochleas work better, or abnormal auditory systems work better. I mean, we're looking at a bunch of different examples. Google and others have worked at, doing speech recognition, converting speech to text for deaf people. And that falls within the rubric of things we're talking about. If you give people a text version of the signal, that gets information across. You don't need ears to understand speech. So in that sense, yeah, we can do better that way, but we're really concentrating on trying to make everybody better. And actually, one thing we learned is it's easier to make things better than it is to match performance. So for reasons I don't understand, when you try to optimize speech intelligibility with these auditory models, that was easier than trying to match existing performance. And again, it's something about the differentiation and the optimization. So maybe we are going towards superhuman, but we're never, as Brian Moore points out, we're never going to make a cochlear implant user better than normal. They've lost too much information, unless you do something weird like speech recognition. So we're concentrating on the 99% of people who are not baseline.
Yes. Okay, great. So if we cannot improve the interface between electrodes and brain, you don't see the models or the pre-processing solving that issue. Are there further questions? Otherwise, I think given the time, we have to stop this tandem of talks. So I want to thank you again for your contribution, and I really love this session, and we can see how to maybe share this recordings, or maybe make clean recordings or something, but explain it without our current mild cognitive impairments, I'd say. But thanks again, and